a bunch of vocabulary, so you're going to have to copy the stuff. But I would listen and maybe just write the kernel of it rather than try to copy everything down, because then you're so busy copying you can't have time to listen. So there's two kinds of angles we're studying: central angles and inscribed angles. A central angle is an angle whose vertex is at the center. Does that make sense? Central angle, a vertex is at the center. So this blue one is a central angle. Okay? An inscribed angle is its vertex is on the circle. And that also makes sense. Think about like every shape we've ever inscribed in a circle. Like, remember when we learned how to inscribe a hexagon? That meant every single vertex touched the circle, right? So the inscribed angle is when the vertex touches the edge of the circle. Okay, so central angles, vertex is in the center. Inscribed angles, vertex is on the circle. Okay, and then an arc is just a piece of a circle. So that could be an arc. That could be an arc. It's just a piece of a circle. Okay? An intercepted arc is a specific piece of the circle. It's the piece of the circle that gets cut out by the angle. So do you see how this angle comes down here and back up here? So it cuts off this part of the circle. We call that part from A to B, we call that the intercepted arc. It's like if you think of that as a piece of pie, it's the crust, right? The intercepted part is between the sides of the angle. And the way we would write that is you'd put the beginning of the arc and the end of the arc, and then you'd put a little arc above it. So that means arc AB. Inscribed and central. So this is also an inscribed angle, okay? Or intercepted arc, what did I say? Intercepted arc. This purple one and this yellow one. Okay, anything that's between the sides of the angle. Okay? Yeah. Are we good? Does someone else have their hand up? Or is that the question they had? That was your question? Okay. Yep. Intercepted arcs work for inscribed angles and central angles. Just a regular arc is just anywhere on the circle. An intercepted arc is the part that's between the sides of the angle. So like this arc is between the green lines, and this arc's between the blue lines, so those would be the two intercepted arcs. Yeah, of course. Can you do it? Okay. Yes. For the purple, for this one? Oh, what it is? I think so. Minor is less than 180, major is greater than 180, and a semicircle is exactly equal to 180. Okay? And then to, like, let's say I said I wanted to talk about arc AC. Well, I could mean this minor arc, AC, but couldn't also you could start at A and end up at C over there, right? It's confusing which one we mean. So the way they avoid that is, if it's going to be a major arc and they want you to go the long way, they'll tell you a point along the way. So this would be arc ADC, because they're telling you start at A, but instead of going directly to C, go the long way through D and around to C. Does that make sense? That's how they'll tell you which way around the circle they mean you to go. Okay? All right, minor arc, major arc, semicircle. Okay, so let's do a little bit of calculating here. The this is a long time ago, back when actually they measured sales on CDs, because nowadays it's all downloads. But when they did CDs, I pulled up the sales for Virgin Records for a month, and 25% of their CD sales were rock albums. Okay, so I want to know the degree of this angle that they made. Okay, so it's 25% of the circle. What degree would that be? 90, right? Because it's 25% of what whole thing? 360. So 25% of 360 would be a 90. Okay, and the other thing that you need to remember, and we'll talk about this again later, but the measure of a central angle, oops, that's an L, and that's an angle mark. The measure of a central angle is equal to its intercepted arc. The measure of the central angle is equal to its intercepted arc. Because doesn't it make sense that if this angle took up 25% of the circle, this would also be 25% of the circle, of the outside of the circle? Okay, so if this is 90 degrees, this is also 90 degrees. Okay, 13% of sales were rap albums. How many degrees is that? Okay, does that make sense? How we change those percentages into degrees? You probably did this in 7th grade when you were learning how to do circle graphs. You probably did it backwards. You figured out what the degrees were with a protractor, and then you turned it into a percent. Okay. All right. Again, I don't know if I would write down all of this, but let me summarize it for you. All this says that the angle, the central angle, the chord that stretches across the angle, and the intercepted arc are all proportional to each other. So if these two angles are equal, then these two chords are equal, and these two arcs are equal. Okay? And it works no matter which of those three pieces you're given. So if I know these two chords are equal, then I know that the angles are equal and the arcs are equal. If I'm given that the arcs are equal, then I can assume the chords are equal and the angles are equal. If you have one piece, you know them all. Okay? Does that make sense? Yes? Right? And the last piece we covered like literally the 3rd day of class. Do you remember I said we're going to talk about this again, and I thought it might be May, but it was early April. Okay, we learned the segment addition postulate and the angle addition postulate and the arc addition postulate. So let's think about the segment addition postulate, because that one's maybe easier. What does the segment addition postulate say? Remember, postulates are those duh statements. They're so obvious. You feel like you don't even need to say them. That makes a postulate. What's the segment addition postulate? Anybody remember? The segment addition postulate says that if you add xy and yz, you get xz. Right? Remember we learned it by part plus part equals whole? Remember doing that? And for the angle addition, we said if you add this angle plus this angle, you get that whole angle. And so for a segment, or for an arc, sorry, we said if you add this arc plus this arc, you get that whole arc. Part plus part equals whole. That's the arc addition postulate. Okay? We're going to do this proof in a little bit. We're not going to do it today because I want to get through these. All right, so let's practice this a little bit. If PT bisects angle RPS, so here's angle RPS, and PT bisects it. What can you tell me about angle RPT and angle TPS? They're congruent because it's bisected, so that means it splits it into two equal pieces. Okay, so if these angles are equal, what about RT and TS? Congruent. What about arc RT and arc TS? Congruent. So if I'm looking for the length of RT, what would I do? Exactly. I'd set 6x equal to 20 minus 4x. Add, and I get 10x equals 20. Divide by 10, and I get x is 2. And then plug 2 in. 6 times 2 is 12. So RT is 12, and TS is 12. But we don't know the measure of the angles or the arcs, but we know they're equal. Okay, it's not like they're all equal to 12, but we know they're equal to each other. Okay? All right, so this one says circle A is congruent to circle B, and CD is congruent to EF. So what do we know about arc CD and arc EF? They're equal. So to solve for y, I would just set them equal to each other. 25y equals 30y minus 20. Add 20 to both sides, subtract 25 from both sides, and I get 20 equals 5y. Divide by 5, and that gives me 4 equals y. And then plug 4 in here. What's 25 times 4? 100. So if this arc is 100, what's this one? 100. So far, so good? Okay. All right, the last thing we need to learn today is the chord bisector theorem. And the chord bisector theorem says that in a circle, if the radius, or like you could discontinue the radius and make it a diameter, so usually if it's true for one, it's true for both, is perpendicular to a chord, then it bisects that chord and its arc. So let's draw a picture of that. If you have a circle and you have a radius, okay, if it's perpendicular to a chord, okay, so that's what it would look, the picture that would look like. If it's perpendicular, then it bisects that chord. Okay, and the converse is true. If the radius is a perpendicular bisector, or if you have a line that's a perpendicular bisector, then it's also a radius or a diameter. Okay, so yes. If the way in a circle, if the radius is perpendicular, then it's a bisector. And if it's a perpendicular bisector, then it's a radius. So both ways you have to know it's perpendicular. Okay? All right? That was a really good question. Did everybody get that? Okay. Okay. So we have this radius that is perpendicular to this chord, and we want to know the length of BD. So think about what you know and see if you can figure out a way to calculate the length of BD.